everyone. Thanks for coming along. So today I'm going to talk a little bit about the new USB device interface that we have in MicroPython. So this has been a long time coming. Angus has been working on this, I think, since October 2022 was when he opened the pull request. So it's been over a year and a half. And the idea with this USB device interface is to give you full access and control over USB peripherals on whatever board you have. I'm going to be demoing with the RP2040 with a Pico. So that has USB. Obviously, you can use usually for the serial REPL, but it can be turned into any kind of USB device. So in USB terminology, the device is the thing that is giving you some services like a mouse or a keyboard. And the host is the other side, which is usually your PC that's connected to the device to. Sometimes the microcontroller can be the host as well if it has host mode, but we don't support that yet. We support only device mode. So you can make a keyboard or a mouse or a MIDI controller or a serial port or anything else, and you plug it into a host like a PC, and the host will control the device or talk to the device. That's basic USB terminology. So this feature aims to be like all the other machine module features that we have, such as PIN and UART and SPI and I2S. And also it's similar in a way to Bluetooth in how it works. It's quite low level with some callbacks. And we tried hard to make the API consistent with other things, but it's hard because it's quite a different peripheral to, for example, GPIO. But it lives in the machine module because it's quite a low level sort of interface. So it's machine.USBDevice, capital USBD device. You can see here. And this will hopefully be, well, this will definitely be in the next release, which is going to be very, very soon. Maybe this week or next week. So you can already start using it, but you'll be able to use it in the release. Now, there's a few things to sort of overview with this when using it with MicroPython, because obviously a lot of boards use the USB for the REPL, and you can't develop a USB device and have a REPL at the same time unless you have two USB ports on the board, or unless you do something tricky to have both a serial port and, say, a keyboard at the same time. And you can actually do that, but it's it's still a bit tricky, because if you keep changing the behavior of your USB device that you're developing, the REPL keeps disappearing every time you change the behavior. So that's kind of unavoidable, because we wanted to make it as powerful as possible so that you can, for example, turn off USB completely. So basically you have full control over USB. So for example, you might want to make a device that just doesn't have USB at all to keep it secure, so it doesn't have a REPL. And maybe you want to turn the USB on every now and then when the user does some particular action, like presses a button. And you can do that with this API. So you can turn the USB off to start with and only turn it on when you want to, and turn it back off again when you're done with it. And you can reconfigure it on the fly, although maybe Tiny USB has some limitations there, which is what we built it upon. But for the most part, you can implement any USB device that you like. And you can read the docs to see what the API is. I'll go through a demo of how to use it rather than explain everything from the docs. But just to show you, there's quite a bit of overview here. But there's really only a few methods you need to know about. The config method, which sets up the descriptors and the callbacks. Then the active method, which turns it on and off once you've configured it. So to re-enumerate, you can active, false, active, true. We'll unplug and sort of replug the device. You can use the built-in driver if you want, like built-in serial. And then there's a method to submit a transfer, like send data to the host, and then to stall as well if you aren't able to send data just yet, but you can later. So there's only a handful of methods to know about. And with that, you can actually make any USB device. So we did spend a lot of time going over the API, trying to make it clean and minimal, yet powerful enough. And on top of this API, Angus has also written a more high-level Python interface that allows you to do things more quickly, like just make a USB keyboard in a few lines of code. But what I'm going to show you today is more the low-level interface and how you can make a USB device that does anything. So there's some more constants. You can read through this documentation if you're interested. It gives you enough information about the interface. But let me flip over here to some code here. So I think we sort of need to jump right into it, explaining how a USB device is described. So when you construct a USB device, you have to tell the host what it is. And there's two main things to do that. First is a device descriptor, which has all this information in here. Basically the vid and the PID, which you're familiar with. It tells you the vendor and the product identification. And then a few other bits of information like the manufacturer and the product name and what version of the USB it supports. So this device descriptor is on every USB device. And it usually has pretty standard values. But you can configure these things however you like. So the class of this device that I'm making here is a vendor-defined class. So I'm just making something that's not like a keyboard or anything. It's just some custom thing. And then the other thing you need to define is a descriptor configuration. So this is a bit longer. And you usually take something that was already done and modify it to your needs. But what it actually has to do is tell the host what its endpoints are, which are sort of the channels across which you can send data. So you need an in usually and an out. And they are with respect to the host. So in means going in from the device into the host, and out means going out of the host and into the device. So there's transmit and receive there. But of course, transmit depends on which side of the line you're on. So they're called in and out to disambiguate that. And the rest of this information here is telling various things like how much power it can draw from the USB port, the number of interfaces it has. So you could have like 3 serial ports and 2 keyboards on one device. And so that would have 5 interfaces then. But here we're just going to have 1. And this interface descriptor is saying, well, for the interface that we're implementing, what's its name? So that's this last entry here. How many endpoints it has is this thing here, and a few other bits and pieces of information. And then it's got to be followed by the actual endpoint information, which is below. So there's a few resources on the internet that you can read to understand these descriptors. Like I said, it's easiest just to get something that is like the thing you want to implement and then copy. What I've got here is sort of the simplest that you can do that will allow you to have 2 endpoints that you can transfer data. So the idea with this example is that it's just going to have an in channel and an out channel, and it can send and receive data to and from the host. So this is sort of the simplest thing you can do. Kind of. You can actually do it even simpler by not having any out points at all, and just use the control endpoint, which is like the default endpoint that everything has to have. I can show an example of that later, but I thought it was more interesting to show something with endpoints. So you have to write these 2 descriptors. Now, in the end, these are just a bunch of bytes. So the first one is only 18 bytes, and the second one is like 18 plus 14. bytes long. So they're not very big. It's just very verbose here because there's lots of comments. The other thing you need is to provide strings. So you can see up here. So this is the name of the interface, but it's actually an index into the string table. So index hex 15 will be a string describing the interface. So if you look down in my string dictionary here, index 15 is iInterface. So when the host connects to this device, you can look up this string index and it will see it's called iInterface. And similarly, I've got strings for the manufacturer, the product, and the serial number. And those are referenced in that top descriptor. So these three entries here. So these are indices again into the string table, 11, 12, and 13 hex. You can make them whatever numbers you like. I just did 11, 12, 13 just to show you what can be done. Usually you probably start at 1, 2, 3. So you've got two descriptors and then a table. Now the USB device interface that we have allows you to provide the strings as a dictionary, which is convenient. You can just map those indices to strings, or you can just provide a list where the index is just the offset in the list. Or you can actually provide a class that implements subscription and the get item method in Python, and then you can actually do dynamic string lookups. But yeah, so you can have basically a callback when you get to string. But for now, we'll just use a dictionary. So these three pieces of information fully describe our USB device. And maybe what I'll do is I'll start it up. Let's come back to the callbacks later on. But down the bottom here is the code to start the device. So you create the device to start with. I'll just put, oops. So you create the device using a constructor, and then we're going to say we don't want any built-in drivers. So we don't want the built-in USB mass storage or CTC or anything. We just want to have our device, and that's it that we've defined. And then we configure the USB and pass in those descriptors that I've shown you, the device, the configuration descriptor, and the string table. We do have a bunch of callbacks. Let me just comment them out to show you that you don't actually need them for now. And then once you've configured it, you activate the device. And this is essentially like plugging the device in. So even though it is already plugged in physically and drawing power, it's not until you do USBD active that you allow the device to be seen by the host, because it pulls the right T+ or D- line in the right direction with a pull up or pull down resistor. And the host sees that, oh, something's connected, and then it will try and talk to that thing. So this code that we have here just sets up these three pieces of information and activates the USB device. And then hopefully if we run this, it should actually work. So I'm going to try, we need kind of 3 screens here. So we've got the code at the top. I need, now for this example here, I'm using a Pico, Raspberry Pi Pico board. And I've actually enabled UART REPL as well as USB REPL, because so that we can see what's happening whilst the USB is working. So down the bottom here, this is a UART REPL. And then in the middle, that's actually the USB REPL at the moment. But we're going to turn that into a USB device. So I'll quit that one. So what I want to do is run MP remote run, and I don't want to follow the output because the serial device is going to disappear in a minute. And I'll run my code. Whoops, I'm not in the right directory. USB device. Okay, so this should run the code that we've just written, or that we've just been looking at, and turn this Raspberry Pi Pico into a USB device that we've defined. Okay, so that worked, and down below you can see the REPL as something's happened to it. We're still got Actually, no, I think I just took it away. Let me. Okay, I just reset that. I'll run it again. Okay. I think if we should still have a REPL here, yeah, because it's just running in the background. And if I do ls_usb on my computer, i.e. the host, I should see, yeah, here. So we've got this thing with iManufacturer and iProduct. So ls_usb is listing all the USB devices that I have connected. And you can see this is the one we've defined. So at the very top of my code, that was the vid and the PID that I used that you see here. And iManufacturer and iProduct are the strings that we defined. So let's change those strings. So iManufacturer, this is the manufacturer string, and iProduct, this is the product string. Okay, so if we reset that and then run it again, and ls_usb, so you can see this is the manufacturer string, this is the product string, so that's changed. So you can see how it's very easy to dynamically create your USB device and change things pretty quickly on the fly. Admittedly, as I said, I've got a UART REPL down the bottom here, just to help me develop. But you don't need that. You can just run it. It's just here for show. So I'll just change those back. And the other thing we'll do, I'll just make this bigger. So I'll show you, if you do ls_usb verbose for this device, this will show you what the host sees from this plugged in device. And this is basically just a mirror of that descriptor tables that I was showing you. So this first bit here is exactly our device descriptor information that we've provided. So that's exactly this first bit here. So it's just showing that the host has been able to read that information from us. And it's decoded it as well. So it's decoded the iManufacturer and iProduct and printed the strings that were associated with that. And then the rest of the information is that second larger descriptor. So the configuration, the interface, and then these here, the two endpoints. So endpoint 81 is an in endpoint and endpoint 1 is an out endpoint. And that should match with our definitions that we have here that I've been using. So when endpoints have the high bit set, they're an in endpoint, and the low bit, if the high bit is cleared, then that just means they're an out endpoint. That's how you can tell the difference. And the max packet size is the maximum number of bytes you can send at once over that endpoint. You can actually write more than that, but they'll be split up into packets of this size. And you have different kinds of endpoints, interrupt endpoints, and that's what this is, or bulk endpoints. Actually, that's what this one is. So you can see it's quite straightforward to define a device, and there's no restrictions here. You can put any information you like in here as long as it's valid from a descriptor's point of view. The first byte here actually is the number of bytes in the descriptor. So already, you've got to make sure it's got the right format there. But put anything in there and put any strings here. And already you can create a USB device just with this simple amount of code. But to actually do something more useful, you then want to enable these callbacks. So the four callbacks that we have, one when the interface is opened by the host, one for reset, one for control transfer, which we won't use now, but that's for the endpoint 0 is a special endpoint for control. And then there's a normal transfer callback, which is for the endpoints that we will be using. So I've made 4 very simple callbacks here, and basically they just print when they're called. And they do a little bit more than that as well. But to start with, they just print. So if we save that and go back to this view here, so reset the board. and we'll run the new device with the callbacks enabled. Okay, I'm not sure why that had a panic. We'll try again. What's wrong? This was really working before. Did I change something? Sorry?
Upset the demo guides.
Yeah, this really, it really was working, and I'm doing a hard reset here. What?
So for those watching, there's quite a bit of complexity going on here, but the complexity is kind of in the USB protocol. Like it's actually, this is, if you ever had to do this in C or any other low-level stuff, this is amazingly easy. So yeah, it looks harder than I think it really is.
I shall. This seriously was just working. Like I tested it before I joined. All right, we'll try the one I'd based it off. It's slightly different. Yeah, that worked. Well, it's different there. No. Smaller strings. I don't know, honestly, but let's go with this one instead. This one works. I will have to look at that later. Okay, so there's really no conceptual difference here. It's still got those 4 callbacks. I was just simplifying it to show you. But okay, so it ran. Let me start it again. So we've got our 4 callbacks here. And they're just printing. I haven't changed anything from before. They're just printing when they're called. And I'll reset the device. So down below again is the UART REPL, and then we're going to run the device. Here we go. Okay. So now we're getting callbacks. So we got the host reset it twice. Don't know why. And then it opened the interface. And the data we get from there is which interface it opened, because you can have multiple interfaces. Like I said, you can be a mouse and a keyboard and a MIDI device at once. And so when open interface is called, it tells you which of the interfaces was opened. And nothing else is happening right now. I've actually still got a REPL here because everything's just running as callbacks in the background. But I'm attached as a device. LSUSB shows this device here with these. This demo has some just random numbers for the string, the product, and the vendor, but that's okay. But this device here can actually do a little bit more because I've set it up so that it can send and receive data on the out and the in endpoints. So when you open an interface, basically you have to prepare to receive data from the host. So you say submit a transfer. So on this endpoint, I'm ready to receive data. And when I receive data from the host, it can go in this buffer. And that buffer is just down here, a byte array of the size of the endpoint that I was talking about before. The max size was 64 bytes. So this, if you don't do this, your device is not ready to receive data. And if you try and write data to it from the host, that will time out. So I'm saying I'm ready now to receive data. And then when I do receive data, I'll get this callback. And if I've received data, then the endpoint that I've received it on is that out endpoint that I've set up. I can print out the buffer because the data was received into that buffer. And then instead of what I could do here, I could say, all right, I'm going to prepare to receive another out packet. And then I only ever able to receive out packets. But actually, what I'm going to do instead is say, I'm going to submit a transfer on the in endpoint to echo data back in. So the first submit transfer was to say, okay, we're ready to receive data, and here is the buffer. But this one here, because it's on the in endpoint, it's saying we're ready to send data, and here is the buffer to send. So that actually initiates a send. Although in USB, the host is always the thing that's controlling it. So the device doesn't send the data, the host requests the data. So here we're just saying, data is ready for the next time the host requests it. And we're going to echo back basically the buffer that was sent and the number of bytes that were sent to us. So we're actually preparing to receive up to 64 bytes, but the host may send less. And the amount that it sent was told us here in xFIRD bytes. And then the last bit of logic is that once we have finished echoing data back again, we get another notification at a callback to say the host has received our data. And once the host has received our data, we're then going to prepare to receive data back ourselves. So basically go back to step 1 to say, okay, now that we've sent our echo, we're going to wait for the next command. So this device is just an echo device. It will receive data and then ping it back to the host. But it has to be in that order because of the logic we've written here. It's only ever ready to receive a packet. And once it's received, it will send it back. And it's not until it's echoed that it's ready to receive another one. Okay, and I can show you exactly how that works. Hopefully, oh gosh. No. Why does, there we go. Sorry. So, all right. We're going to run, I think this device is already running, isn't it? Yes. Okay, so we're going to try and run Python. Actually, I need sudo to access this. Okay, so we're going to use Python, normal Python, as the host. And I need some help here because I don't know all these commands off the top of my head. So I've written some stuff here, but we want to use the USB driver. So this is nothing to do with MicroPython. This is CPython and PyUSB. Okay, so I'm on the host. In this middle terminal, I'm now the host. The bottom one is the device. I think I'll need to define my vid and pid, and then need to connect to the device. Okay, so this command running on the host will connect to the device with the given vid and pid. Okay, that worked. So now what we can do, we have to claim an interface. So you saw before that I said we can define a mouse and a keyboard and everything in one. Well, you've got to say which one you want to use. So we want to use interface 0 because there's only one interface on this device. So we'll claim that interface. And now the next thing we can do is say read the strings. We don't need to, but let's see what happens. So we can read strings from the device. So remember we called it hex 11 was the manufacturer string, which actually is AO21 in this example, or hex 12. And actually I've defined all the strings on this one. So string 1 is A1, string 2 is A2, and so on. So you can see I can read strings this way. That can be useful sometimes because some strings you can actually store information in. But that's just showing you how the host can read stuff. Okay, so now we'll try and do the interesting thing and actually write data. So remember, the device was primed to receive data from the host. So the host can do a write on the out endpoint, and I think that's OX81. No, OX1. Otherwise it would be wrong. Hex 01. Okay, so we'll write data to the out endpoint, and we can write whatever we like. So let's write hello from host. And we'll see when I run this, in the terminal below, we should receive a callback with that data. Okay, so that was correct. So on the host, the 15 means we wrote 15 bytes successfully, which is how many bytes was in that string. And down the bottom, you can see it got the transfer callback. And if I go back to the code, what are the numbers it's printing out? So it's printing out the endpoint, endpoint 1, which was the in endpoint that we sent on here in the device, in the host code. Result 0, I think, I'm not sure what that means. It would be in the documentation, but 15 is the number of bytes. 0 actually might mean the stage of the, oh no, okay, look that up. So we got 15 bytes, and that was placed into the prepared buffer that we'd already made. And printing out the whole buffer, you can see that only the first 15 bytes were populated by the message. The rest of the buffer remains in its default state. And so now, after receiving that data, the device has echoed it back, but it hasn't been echoed back yet because we haven't initiated a read. And I'll show you if we try and write again, it has an error, a timeout error, because the device is not ready to receive again. So what we have to do instead is read. So read, you've got to read from endpoint 81, which is the other one. And let's try and read 64 bytes and see what we get back. Okay, so we actually just got back the hello from host. That's just in hex. If what I don't know, can we make that into a bytes? Yep, there you go. So we got back hello from host. Even though we asked for 64 bytes, we only got 15, and that's because in the code we'd written, we only echoed back the number of bytes that we received. Okay, so the other thing we also got back was a callback on the device to say that endpoint hex 81, which is 129 here, has finished writing 15 bytes. So we now go back to the state where we're ready to receive data again, because the device executed this command here. So we can, if we try and read again, we get a timeout because there's nothing to read. But if we try and write, so it's hello from host again, then that gets through. Hello from host again gets sent through. And then when we read it back again, bytes, that we get hello from host again. So this is really all there is to it, to making a USB device, sending data back and forth between endpoints. You can obviously make your logic a lot more complicated, add more endpoints, allow to receive and send at the same time. You know, there's lots and lots of things you can do. So we can change this quite easily here. So instead of echoing data, let's just go straight and allow to receive data again. So we're not going to be an echoing device. We're just going to be a receiving device. Okay, and then if we go into Python, should be quick to run this again. Find the device. Yep, the device is there. Claim its interface. Good. And then we should be able to write to endpoint out, which is hex 01. So test. And we can write test again and again and again and again. So all our device now is accepts strings again and again. And if we try and read, then it's just going to time out. We're never able to read. So you can see how quickly it is that you can change the behavior of your device in Python. We could also, because we actually have a REPL here, we could actually, I could actually submit a transfer here to say, what's the endpoint again? 81. So this is a message. Okay, so now we should be able to do a read, and get this as a message back. So you can see just from the REPL, I can actually submit the transfer. So even though I've got my logic here to be always a receiving device, I can actually send a message as well. So you can play around a lot with USB doing this. So that's really the overview of how this all works. You can see that it's quite powerful, that there's not much to this example, a couple of descriptors, a set of strings, and 4 callbacks, and then also this submit transfer method. We didn't use stall. That's to say, that's when you say, oh, I've got data, I will have data in the future, but I'm not ready yet. So the host will stall and ask you again later. And we also didn't look at the built-in device support, but I won't have time to do that now. As I said, Angus has also written a higher level API, so you can just instantiate a keyboard, for example. But if you want to play with low-level USB and write your own USB device, this is the way to go. I have also written a DFU driver, which I alluded to before. It doesn't use endpoints, it just uses the control. So here you can see in this descriptor, there's no endpoints. It just uses the control endpoint, the default control endpoint. There's no additional ones.
That's really good.
And you use the control transfer callback for that, which we also didn't really go into. So that's that's another, well, that's part of the USB standard. And like if you wanted to implement a USB serial device, a CDC device, you'd need to have control transfer and normal endpoint transfers as well. The control transfers do certain things, and the endpoint transfers actually transfer the data. So yeah, you can invent whatever USB device you like. And this code here I'll publish, the DFU code will go on GitHub soon as an example, but it implements a full DFU device. I think if I actually run that now, the reset and run USB DFU. All right, so now it's acting like a DFU device, and if I go PYDFU list, yeah, so there's a device here, and I can upload to the device, say, doesn't matter, some DFU, random DFU file. So here it's actually transferring what you just saw then. I can do it again. Even though nothing's happening down below, it's actually transferring data to the device there. It just downloaded 30K in that time. So it's actually pretty quick. We could print maybe some status information, but let's see, control transfer. That'll actually probably be pretty noisy, but if we run that again, and then when I upload that file, you should see lots of information down below. Yeah, so you can see it's a lot slower now because it's printing out whenever it's getting a control transfer. And some of those control transfers have 2K of data associated with them. So there's a lot going on. So that's it. Hopefully that gives you a good overview of this new API. Go back to these docs. Yeah, I think it's really great. I'm very happy with how it's turned out, because it's basically you can write whatever device you like in Python. And yeah, this will be available in the next release, 1.23, which should come out in the next week or so. So
Cool.
it's me done. Any questions I can take? Oh, I know that took a while, but I think there's maybe time for questions.
Yeah. Everyone follow that?
Yeah, I got a question, Damien.
Yeah.
Just with the fact we've just got the one link with the REPL and the CDC like UART port. I saw there's some demos in Tiny USB for dual CDC, or two, where it implements two serial ports through the single USB cable.
Yes.
And so I'm just wondering, like, whether it'd be useful to just have one which is just permanently the REPL and the other one that you kind of send your data across, and whether this could be adapted that far with what's already in there, or would it be?
Yes. So this is something I didn't touch on, but so what you can do, you can go USB built-in driver is built-in CDC.
Yep.
So that basically puts the serial CDC stands for Communications Device Class. I think that's a serial port. So it puts the serial port first, and then any interfaces after that are the ones you define. So you can basically append your device to a serial device, and the serial device is the REPL, and then you've appended your DFU or custom device after that.
Okay, awesome.
So it does support this feature, yes. And yeah, Angus spent a lot of time making that work. I wanted to try and keep things simple with this demo, but you can do that, except the thing you have to be careful of is that you your endpoints have to be different because they can't clash with the built-in endpoints.
Yeah.
And I think the way, like, the numbers that you put in here, the interfaces have to change. I can't remember the details, but you have to fiddle a bit with these numbers so that because these numbers here assume that it's the only device. But if this sorry, the only interface on the device, but if you've already got a serial port and you're adding this to the serial port, you just have to adjust some of these numbers to take that into account.
Okay.
But yeah, that is definitely doable. And then dual CDC, yeah, I mean, you could have 2 CDCs and a keyboard and a mass storage. You could implement all that yourself, and the CDC could be built in. So there's lots of things that can be customized.
Right.
So, yeah.
That's cool. How far away is that? Anyone else have any questions? Or cool. Thank you, Damien.
Yeah, that's awesome. I'm making a USB keyboard now.
Yeah, I think everyone wants to make USB keyboards with MicroPython. So
I know. Even I do want to do this. Yeah, I have a keyboard that I need to customize. Yeah, so that, as I said, there'll be some code in MicroPython lib to make that really quick and easy. But yeah, and it'll be easy to have it be a keyboard and a serial port, so you can have a REPL and a keyboard.
You can use the keyboard to talk to the keyboard.
Indeed, yes. Or the keyboard to talk to the mouse. Yeah, that's cool.
there's a couple of comments in the chat. Patrick's asking how the underscore works in bytes underscore.
Oh, that's just the Python trick. Underscore means the result of the previous expression.
Okay.
So in that case, I'd made like
Sensitive.
yeah, I'd received something and then I just turned it into something. Yeah, underscore is just the previous expression. This previous expression's written result.
That's good to know.
And Mike wants a USB webcam that streams a video of the REPL. Yeah, I like the idea. It's a good idea.
Streams of video.
So you generate a video stream. Yeah, it's great.
You could, because you could.
On the other end.
Thanks, Mike. Damien's going to be not be able to sleep tonight. Like,
yeah, that's actually it's not too hard because you don't need much data because you can just generate the image on the fly, right?
Just
and
because it doesn't mean you should. Yeah.
And webcams can be like an arbitrary resolution, so you could just be like 10 by 10 pixels. That would be actually.
I like an MJPEG thing that doesn't have to be a high frame rate.
I think that's 7 minutes. Cool. Thank you, Damien. Thank you very much. That's great. I'm looking forward to playing with this. So yeah, it's very cool.